Alright, let's go ahead and get started. So, happy Friday. Any questions on anything you guys want to talk about? Alright, cool. So just a couple quick announcements. Next Mondays there's going to be a quiz. That covers lessons 21 and 22. Quiz 9 is going to be not this Friday, not today, but the Friday of next week, covering lessons 23 and 24. So, yeah, that's about it. Anything else? Any other pressing homework matters you would like me to attend to? Okay, cool. Alright, so today we're basically going to take everything we know and regarding the past few lessons and basically put it all together. So, lesson 23 is basically the summary of curve sketching. So basically we're going to take all these concepts we learned about for the past several lessons and we're just going to apply them to actually be able to draw a rough sketch that's a bit more precise than you probably would have seen before. So basically take these pre-established properties to draw a sketch of the graph of f of x. So start off, x-intercepts. So points of the form x comma 0. Okay. And if you want to figure out how to get x-intercepts, you solve f of x equals 0 to find them. So to do that, we can say, all right, well, we have to check the numerator of the simplified form. Simplified form of f of x. Okay. Now, the nice thing is the y-intercept is slightly easier to find. So, in this case, you're just going to have a point of the form 0 comma y, where in this case, if you want to figure out y, well, just take our function f of x, and let x equal 0. So there's that, and then increasing and decreasing intervals. We have, alright, well, for increasing we have f prime of x has to be greater than 0, and decreasing, similarly, is where f prime of x is less than 0. And regarding concavity, we have where f double prime of x is positive, concave down is where f double prime of x is negative. And inflection points are where concavity changes. Okay. So that's basically 1 through 7. So what I'm going to say from this is that we say, all right, so one thing to keep in mind for 1 through 7 in particular is that these 7 have to be in the domain of f of x. So must be in domain of f of x. Okay. So that's the first 7, and then the last 3 are basically stuff we talked about last time. So the vertical asymptotes, or vertical asymptote, are zeros, or 0, depending on the number. Zeros of denominator of simplified. Simplified f of x. And as we talked about last time, this will correspond to x equaling some number. That's what the form of a vertical asymptote is. Okay. The horizontal asymptote, meanwhile, you have to focus on if L equals the limit as x goes to plus or minus infinity of f of x is finite, then y equals f. Okay. And so the nice thing is generally with these types of problems, if the limit is going to be finite, usually the limit as x goes to positive or negative infinity is going to be the same if we have finite L. And that does hold even if L is 0. Okay. Slant asymptotes, that's the line y equals mx plus b if the degree of the numerator is precisely 1 greater than the degree of denominator. Okay. So basically that's just a quick little review of the stuff we've already seen up until this point. So nothing too crazy with that. So one quick little remark before we move on to our examples for today. So when curve sketching, it's best to plot/sketch intercepts / asymptotes first, and then we use intervals in 3, 4, 5, and 6. So basically these intervals up here to draw a sketch of the graph of f of x. So one thing to note here is that determining the graph of f of x will most likely correspond to a multiple choice problem on definitely a homework and very likely on a quiz or exam based on the nature of the material covered. So the thing is, your graph sketch does not need to be extremely precise. So the thing is that, for a lot of these, you could probably say, all right, well, once I have enough properties, I could sort of, go by process of elimination to sort of see which of the graphs given to me satisfies these properties. But for now, what we're going to do is we're going to focus on, taking all these properties and drawing a sketch of it so that way you know how to do it, how to draw a sketch of the graph without giving any choices. So that's going to be our focus for today. So let's go ahead and do that. So taking example 1. So here's what we're going to do. So we have this function given to us as x squared plus 3 divided by x squared minus 9. So basically we have to find the following 10 things that we just established, if they exist. And we have to use these to sketch the graph of f of x at the bottom of this page. So here's how this is going to work. So basically this page here is going to be, here's all the points / intervals or line, whatever. And then here's going to be where our graph's going to go. But this page, on page 3, is going to be our scratchwork page. So just to make things a bit more sort of organized. So just something to keep in mind here. Okay, so let's start off by going down the line of each of the things we're asked to find here. So let's focus on the x-intercepts. So with this, okay. So with f of x, so starting off with 1, so we have to find the x-intercepts. So here we have, all right, so solve f of x equals 0, which is just x squared plus 3 over x squared minus 9. So if you take a look at the top and bottom here, well, is this already simplified? As in, are there any common factors between the top and bottom? So, who says there are? Who says there are not? Okay. So just a quick review, what I mean by factors is that one thing to note here is that with, say, x squared plus 3, well, you can't really factor this, so that's out. But the bottom can be factored as x minus 3 and x plus 3. But none of these can cancel out with each other, so this is as simplified as it gets. So in this case, as per our discussion from earlier, we just have to check the numerator. So x squared plus 3 equals 0. So if we try to solve this, well, what happens?
We get negative square roots.
Yeah, we get
Square root of a negative number.
yeah, square root of a negative number, which is not something on the real line. So in this case, no real roots. So no x-intercepts. So because of that, we're going to go ahead and put none right here. Okay. So that's the first part. So now 2, we're going to go and focus on the y-intercepts now, or in this case, just the y-intercepts. So as we said in our discussion, well, all we have to do is just let y equal f of 0 to get our y-coordinate for our y-intercepts. So for y-intercepts, let's go ahead and say, all right, if we let x equal 0 right here, well, what fraction should we get? Yep, negative 1/3, because if you just let x equals 0 here, you should be able to pretty quickly see that this is just 3 over negative 9, which simplifies to negative 1/3. So then because of that, well, that means your point, or y-intercept, is going to be 0, negative 1/3. Okay? So that means your y-intercept, we're going to go and put on page 2, 0, negative 1/3. Okay. So now with the next two, we're going to focus on them back to back because of the fact that we usually find increasing, decreasing intervals together. So 3/4. So we have increasing / decreasing intervals. Okay, so based on what we've established and sort of based off of work we've already done before, we have to focus on when the first derivative is positive and negative to get the increasing, / decreasing intervals respectively. So, because of that, we have to first find f prime of x. So, if we take our function here, so how would we find the derivative of this? Yeah, quotient rule, because remember, we got one function divided by another function of x, so that's our quotient rule coming into play here. So I'll go ahead and say use quotient rule. Quotient rule. So if you guys use quotient rule on this, then what should you get immediately from applying the quotient rule? So I'll give you guys a second to find that. So if we immediately apply quotient rule to this, then what should we get as our derivative? Go ahead.
Negative 12x over square root of 9 square.
I would say don't simplify quite yet. Let's just focus on what the what quotient will immediately give us?
Okay, x squared minus 9 times 2x minus x squared plus 3 times 2x all over x squared minus 9 squared.
Yep. X squared minus 9 20 squared. So just a quick review of this. Remember, quotient rule says, so this is low and this is derivative of the high function. So low d high, and then minus high d low, so derivative of the lower function, all over low squared. So just a quick little review of the quotient rule. It says low d high minus high d low all over low squared. So where low is the denominator and high is the numerator. So just a good old quick review of that. So now that we have that, let's say, all right, well, if we go ahead and distribute the 2x into both terms and simplify as much as we possibly can, then what should we get as our simplified numerator?
Negative 12.
I'm not getting negative 12x.
I got negative 24.
24x, right? Because the thing is that the x squared, essentially the x cubed terms are going to cancel each other out, so those are gone. But then we have negative 9 times 2x, so negative 18, and then minus essentially 6x. So that means we get negative 24x out of this. So negative 24x over x squared minus 9 quantity squared. Okay? Okay, so now we say, all right, so remember, if you want to find the increasing, decreasing intervals, we first got to work with the critical points. So one thing to note here is that, so if you want to find the critical points, remember that means basically they correspond to x values that satisfy what? The derivative has to, where such that the derivative has to be either of what two things? So for critical number, we say, all right, it's an x value that gives either the derivative is equal to what or what. So I guess we'll go ahead and say this note, and then we'll go ahead and focus from that. So for increasing / decreasing intervals, and concavity intervals. So one thing to note here is that in this case, what you notice is that in this case we will have to worry about dividing by 0 here. So x values not in domain can't be in final intervals. So for now, we're just going to include all x values for now where we have a critical point. So if you recall, that says, okay, the derivative either has to be equal to 0 or the derivative cannot exist. Okay? So if you take a look at this sentence, we have to make sure we cannot include x values that are not in the domain. So before we move on, we should probably check to make sure, well, what is the domain? So if we check the domain of our original function here, well, what would be our domain of this?
Negative 3, positive 3?
Yep. Well, they can't be either.
They can't be.
Yeah. Because if you take a look at the denominator, what you notice is that, well, the only problem we could potentially have is dividing by 0. So the only way we can get that is if we have plus or minus 3. So this would be our domain of f of x. Okay? Okay, so now that we have that, we say, all right, now that we have our derivative, now let's focus on when the derivative either equals 0 or it does not exist. So first off, when would the derivative equal 0? When would this derivative equal 0?
At 0.
Yeah, just x equals 0, right? Because of the numerator, because, well, the only way you can have this equal to the numerator equals 0 is if x equals 0. Right? But now what about for the derivative not existing? So, in this case we should end up with 2 values because of the denominator, right? So what 2 values would those be?
3 and negative 3.
Yep, again, just plus or minus 3, right? Because x squared minus 9 equals 0 is the same thing as x equaling plus or minus 3. Okay? Alright, so for now, let's go ahead and draw our number line corresponding to the first derivative. So we have f prime here. So we got negative 3, we got 0, and we have 3 as our critical points. But here's the catch. Well, at least for now we include them as x values where the derivative equals 0 or does not exist. So what we're going to do is say, all right, well, because f prime equals 0 at x equals 0, we're going to have a little 0 up here. But then because the derivative does not exist at plus or minus 3, we're going to put a little x here to denote the fact that it does not exist. Okay? So now we go ahead and apply our usual procedure of, well, checking a point inside each of our given intervals and see, does it give us a positive or negative value at our given points. So in this case, let's focus on, let's first focus on this interval here from negative infinity to negative 3. So if we plug in a value from this interval into our derivative up here, then are we going to get something positive or something negative out of this? So if we focus on negative infinity to negative 3, and we plug in a point there,
You get positive.
yeah, we get positive, right? So if you want to plug in, say, x equals negative 4 into your derivative, then a quick little bit of numerics here should tell you that you should get something positive, something positive out of this. So that would give you that you should have something positive here. Okay? Now let's do the same thing with going from negative 3 to 0. So if you plug something in from that interval, what happens? Positive or negative? We get positive, right? Okay? And then from 0 to 3, what happens?
Negative.
Yep, negative. And then 3 to infinity? So, yeah, negative. Okay? So the nice thing is that since this all corresponds to our first derivative, that means that, well, as we had just established up here, well, increasing means the first derivative is positive, so because of that we're going to put a northeast pointing arrow here, and then for the decreasing intervals where the first derivative is negative, we're going to put a southeast pointing arrow for these two intervals. Okay? Now, the thing is that, as we've sort of done before, the thing is that normally if x equals plus or minus 3 were inside our intervals, the increasing interval in that case would be from negative infinity to 0, and the decreasing interval will be from 0 to infinity. But the thing is that, remember, plus or minus 3 is not inside our domain, so we have to be careful here. So because of that, we actually do need to have two separate intervals because plus or minus 3 are not in our domain. So because of that, we have increasing is going to be from negative infinity to negative 3, and negative 3 to 0. Okay? Because like I said, normally if negative 3 were inside our domain, this would be negative infinity to 0. But because negative 3 is not in our domain, we do actually have to separate this time. Okay? And similarly, decreasing is going to end up being from 0 to 3, union 3 to infinity. Okay? So, let's go ahead and put that into our page 2. So we have increasing intervals is going to be negative infinity to negative 3, union negative 3 to 0, and 0 to 3, union 3 to infinity for our decreasing intervals. So that's 3, and that's basically the next two. So any questions on any of that before we move on?
Will we have to do that in one Catholic too?
Yes. Yeah. So like I said, if negative and positive 3 were in our domain, yeah, we would mesh them together, but because they're not in our domain, we do have to separate them out this time. Okay. So now let's move on to the next two, so our concavity intervals. So the nice thing here is that basically we have to do a similar analysis as we did in 3/4, except now we have to do it with the second derivative. So 5/6 are concavity intervals. Okay. So as we had before, well, first we gotta find. Oh, yeah, sorry. First, find the second derivative. Okay, so the thing is that basically we just take our, so if you want to find the second derivative, well, it seems like we got to apply quotient rule again, right? So what I'm going to do is I'm just going to say for now, I'm just going to just tell you what the second derivative is after applying quotient rule and doing all the simplification. So I'll just say for now, I'll say quotient rule, and simplification. Okay. Just to make things a bit, just so you guys have a second derivative down. So what we're going to do is I'm just going to say, once you do all the quotient rule and simplification, I would say check this on your own. Though I do have the notes, I do have the work in my notes, so you can check that later just to check. But your derivative should ultimately be 72 times x squared plus 3 over x squared minus 9 quantity cubed. Okay. So I'll say, yeah, check this on your own, but this is what you ultimately should have as your second derivative. So as we had in our note up here, in finding the increasing/decreasing intervals, what we have to do is say, all right, as we had with decreasing intervals, we got to focus on where, in this case, the second derivative either equals 0 or does not exist. So again, check, or not necessarily check, but in this case we're going to include all x values where f double prime of x equals 0 or does not exist. So if we take a look at our second derivative here, what values of x I give us either a second derivative equals 0 or does not exist? Go ahead.
Minus 3.
Just minus 3? Okay, sorry, I only heard minus. I'm like, what? There
No,
should be two of them. But yeah, no. So the thing is that because of the numerator, the fact that this x squared plus 3 does not have any real roots, as we established in step 1 of part 1, that means we don't have any values where the second derivative equals 0. So our only focus in this part is going to be where it does not exist. So, okay. So, now let's go ahead and draw our good old number line for the second derivative. So in this case, we have -3 and +3. And because the fact that the derivative does not exist there, we're going to include x's as we did before. Okay? So in this case, now our intervals of consideration are going to be from -infinity to -3, -3 to +3, and then from 3 to infinity. So in this case, let's start off with -infinity to -3. If we plug in a point, just any x value you want, into the second derivative, are we going to get something positive out of this or something negative? Yeah, we're going to get something positive out of this, right? Because if you plug in, say, -4 again, so if you plug in -4 into our second derivative, you should get something positive out of this. So there's that. And then I'm also going to, because we're working with concavity here, the fact that we have the second derivative is positive means we're going to have concave up. So I'm going to have a little happy face here to indicate that. Okay. So now let's focus on negative to positive 3. If we pick a point in that interval, are we going to get something positive or something negative out of this? Raise your hand if you... Negative, right? Because if you plug in, say, x equals 0, then you should be able to pretty quickly see that the numerator is positive while the denominator is negative. So we get something negative here, so we're going to have a little sad face to denote concave down. And then for 3 to positive infinity, are we going to get something positive or negative for our second derivative?
Negative.
Negative?
Positive.
Positive, good. Okay. So again, include a happy face here to denote concave up. Okay. So after all that, that should pretty quickly tell you that your concave up intervals are going to be from, so concave up and then concave down. So that means for concave up, well, that means that we're going to have that these two intervals here are going to correspond to our concave up intervals. So we have -infinity to -3 and 3 to infinity, while concave down is just negative to positive 3. Okay. So that's our concavity intervals. And we will also put that up here to denote that. So concave up is, let's see, as we established, so -infinity to -3, union 3 to infinity, and concave down is from -3 to positive 3. Okay, so that gives us our concavity intervals. So essentially that's a lot of the nitty-gritty work of our problem. So from here on out, the computations get a lot easier. So with 7, with inflection points, so if we take a look at this number line here, where does our concavity change? Yep. So concavity changes. Yep. X equals plus or minus 3, right? But remember, if we take a look back at what we had from first page, remember our inflection points have to be in our domain of f of x. So does that mean we can include these inflection points as inflection points? We can't. Nope. So these are not in our domain. So no inflection points. Okay. Okay. So our inflection points are just going to be big fat none. Okay. So now that's 7. Now let's move on to 8. So in this case, we have our vertical asymptotes. Okay? So the nice thing here is that we again already have that f of x is simplified here. So all we have to do is focus on the zeros of our denominator of our function. So we take a look at our denominator. We say, all right, well, you recall that's the denominator is just x squared minus 9. So x, we just take the denominator and set it equal to 0. So, as we have already established, the x squared minus 9 equals 0, as we already established. That happens when x equals plus or minus 3. So, because of that, that will immediately give you your vertical asymptotes. So, they're going to be x equals negative 3 and x equals positive 3. So there's that. And then for 9, our horizontal asymptotes. So horizontal asymptotes. As we talked about in page 1 here, we have to focus on the limits as x goes to positive infinity of our function. So x squared plus 3 over x squared minus 9. Okay? So if we employ the same trick that we talked about last time, then what should we get as our limit as x blows up to infinity? Yeah?
1.
Yeah, just 1, right? Because remember, in this case, if you let x blow up to infinity, essentially the only dominating terms we care about here are the leading ones, right? So if x goes to positive infinity, we just have essentially just x squared over x squared, but this is just a big fat 1, right? Because they cancel out. So the limit as x goes to infinity of just 1 essentially. So in this case, because if this is constant, that means your limit is essentially going to be 1. So that means your horizontal asymptote is just y equals 1 here. Okay. And then the nice thing is that even if you let x go to negative infinity, the exact same work will still lead you to 1. So in this case, you have that your horizontal asymptote is y equals 1 here. Okay. So the last thing I want to focus on is the slant asymptote. But remember, generally the general rule of thumb is that you cannot have both a horizontal and a slant asymptote at the same time. So since we already have a horizontal asymptote, well, there can't be a slant asymptote, right? So, and we can also, and if you want, you can also use the rule that we have here of, if the degree of the numerator is exactly 1 greater than the degree of the denominator. But since these two degrees are both the same, that's obviously not true. So that means your slant asymptote is a big fat 9 here. Okay? Okay, so here's what we're going to do with this. So before we move on to sort of giving a curve sketch, so even though these are essentially the 10 things that you would need to put in log kappa, one important thing that could help here is, even though this is not anything you need to put in log kappa, here's a quick little remark that could be useful. So So it can be important to check where, if it at all, the function hits the horizontal asymptote, because it's possible that could happen. So where, if at all, f of x touches the horizontal asymptotes, or slant asymptotes, depending on if that exists or not. Okay? So the way we do this here is we say, all right, well, basically we have to take the function and basically equate it with the numerical value corresponding to our horizontal asymptote here. So what I mean by that is our function was x squared plus 3 over x squared minus 9, and the numerical value corresponding to our horizontal asymptote was just 1. So let's equate them to see if, if at all, the function ever touches the horizontal asymptote. So if we take x squared plus 3 over x squared minus 9, set that equal to 1, what we're going to do is we're going to take our x squared minus 9 and multiply it over to the other side to get x squared plus 3 equals x squared minus 9. So we say, all right, from this equation here, are there any x values at which this equation is satisfied? Good. Why not?
Because the x's cancel out.
Yep. The x's cancel out, so you're just left with saying, okay, if there ever is a point at which the function ever touches the horizontal asymptote, that means this would have to happen, but that never can happen, so there's nowhere where the function touches the horizontal asymptote. So no points. So no points where f of x equals horizontal asymptotes. So because of that, f of x doesn't touch horizontal asymptotes. Okay? So just a quick little remark to have, but yeah. Okay. So now that we have all of that, let's go ahead and put everything together. So before we do that, any questions on any of the scratch work here? I know there's a lot, but yeah. Okay. All right. So now that we have all that, let's go ahead and focus now on page 2. So now we have all the answers filled in here. So now let's use this to sketch a graph here. So what we're going to do is we're going to bring back our number lines for our increasing, decreasing intervals, as well as our concavity intervals. Okay. So we got -3, we got +3, and we got 0. So if we do what we did back in lesson 19 and sort of put these number lines side by side and put dotted lines to indicate where there's a critical point, or where the increasing, decreasing, and concavity changes. What we notice is that, well, with the first derivative, we already established the increasing, decreasing intervals. So let's go ahead and redraw those. And then we also have our concavity is concave up, concave down, and concave up. Okay? So the reason why we did this is so that way we can sort of, use this as an immediate reference so we don't have to flip between page 2 and 3 all the time. So now that we have this, let's go ahead and draw our sketch of the graph. So we got x, we got y. So I'm going to have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? So, as per our remark that we established at the start of the lesson, it's good to draw the intercepts / asymptotes first, and then use our concavity and intervals and increasing, decreasing to fill in the rest. Okay, so our asymptotes, so let's see, the vertical asymptotes were -3.
Negative.
What's that? Okay. So our vertical asymptotes were -3 and +3. Our horizontal asymptote was y = 1, so it's just going to be this horizontal line right here. Okay, so now that we have that, we also have the y-intercept was 0, -1/3, so it's going to be right about here. Okay, so now that we have all this, that says, okay, now that we have our x-intercepts, we got our x-intercepts, we got our asymptotes, we got our y-intercepts, etc. Now let's go ahead and use this number lines here to sort of figure out patterns. So what this says is that from -∞ to -3, we got concave up and increasing. -3 to 0, we got concave down and increasing. For 0 to 3, we got concave up and concave down and decreasing. And for 3 to infinity, we got concave up and decreasing. Okay? So to start off with, we're going to focus on negative to +3 first. So for concave down and increasing, what that says is that for here, essentially our graph is going to look something like this, essentially, from -3 to 0. And then from 0 to 3, we have concave down and decreasing, so that means our graph is going to look something like this, essentially. Okay? So that's going to be from negative to +3. So now let's go ahead and use our concave up and increasing / decreasing intervals here to see what our graph looks like. So the thing is that if we were to plug in a point from either of these intervals into f of x, then let's go ahead and plug in, say, x = 4 into here. What would be if we plug in x = 4 into f of x? So if we plug in f of 4 here, what we're going to do is because of the horizontal asymptote here, we're going to check to see if this is actually going to be greater than or less than our vertical asymptote, so that we know where it's supposed to land. So if we plug in f of 4, then should we get something that's greater than 1 or less than 1 in terms of a fraction? So if we plug in 4, we have x, so we have essentially 16 plus 3 over 16 minus 9. So is this going to be greater than or less than? Greater than 1, right? So that means our graph is going to be, from 3 to infinity, is going to be above y = 1. So the fact that it's concave up and decreasing means your graph is going to look like this. And then similarly, since f of -4 is also greater than 1, so that means that from -∞ to -3, your graph is going to be above y = 1. So the fact that it's concave up and increasing means your function is going to look like this on that part of the interval. Okay? So that's all I have for today. So any questions on any of that? Okay, good. So I did have an extra example, but didn't really have time to cover it. So I'll just say, check my notes on my webpage and you can see it there. But otherwise, yeah. Hopefully this is a good, insightful lesson on how to sketch a graph using calculus. So, yeah. All right. Well, other than that, I guess unless you guys have any more questions, I will see you guys on Monday when we start talking about optimization for the entirety of next week. Oh yeah, sure.
When's our next quiz?
Next quiz is next Monday.